Hey everyone, Hihu here from LeetCode. Today we're solving LeetCode 345, reverse vowels of a string, using Java. This is an easy difficulty problem, and it comes under the 2 pointers category in the LeetCode 75 study plan. Now the title itself is quite interesting. We've got a string, we've got vowels, and somehow we need to reverse them. But what exactly does that mean? And is there a smart way to do it? Let's find out. We're given a string S. Our task is to reverse only the vowels in the string, then return the modified string. Now when we say vowels, we mean A, E, I, O, U, and their uppercase versions as well. Every other character should stay exactly where it is. The statement is pretty simple, but it becomes much clearer with an example. Let's take the string hello first. Let's identify the vowels. Alolo, the vowels are E and O. Now if we reverse them, they simply swap places. He ololo E, and that's our answer. Let's look at one more example. Suppose we have LeetCode. The vowels are E-E-O-E. Now reverse them. E-O-E-E and place them back into the string. L-E-O-T-C-E-D, which gives us liotseed. So notice something important. We're not reversing the entire string. We're only reversing the vowels. Everything else stays exactly where it was. Now that we understand the problem, let's think about solving it. Imagine you're solving this on paper. What's the first thing you'd do? Most people would probably find all the vowels first, because the consonants never change. Let's try that. For the string hello, we collect all the vowels. E, O. Now reverse them. O, E, and then put them back. That's it. So our brute force idea is step 1, collect all vowels. Step 2, reverse them. Step 3, place them back into the string. Simple and easy to understand. Now let's see how that idea looks in code. We'll start by traversing the string. Whenever we find a vowel, we store it in a list. By the end of the traversal, the list contains all vowels. Next, we reverse that list. Now we'll convert the string into a character array. This allows us to modify individual positions. Then we'll traverse the string again. Whenever we encounter a vowel position, we replace it with the next vowel from our reversed list. Finally, we convert the character array back into a string and return the answer. Let's run this approach on hello. During the first traversal, we collect E, O. After reversing O, E, now we start filling them back. The first vowel position gets EO, the second vowel position gets E, and the final string becomes H-O-Lolo, E, which is exactly what we want. So the solution works. But there's something interesting here. Let's analyze the complexity. We traverse the string once, then reverse the vowel collection, then traverse the string again. Overall, the time complexity is O of n. That's actually pretty good. But what about space? We're storing all vowels separately. So the space complexity becomes O of n. And that's where the optimization opportunity comes from. Let's think about what's really happening. The first vowel swaps with the last vowel. The second vowel swaps with the second, last vowel. The third vowel swaps with the third, last vowel. Notice the pattern. We're working from both ends of the string. And that's a very common clue. Whenever elements near the beginning need to interact with elements near the end, 2 pointers are often a great choice. And that's exactly what we'll use here. Instead of storing all vowels, let's work directly inside the string. We'll place one pointer at the beginning, and another at the end. The left pointer moves forward, looking for a vowel. The right pointer moves backward, also looking for a vowel. Once both pointers land on vowels, we swap them. Then move both pointers inward, and continue the process. This way, the vowels get reversed automatically. And we don't need any extra storage. That's the key idea. Now let's see how we implement it. We'll first convert the string into a character array, because strings in Java are immutable. Next, we create 2 pointers. Left starts at the beginning. Right starts at the end. Now we'll keep running a loop. as long as left is smaller than right. If the left pointer is not on a vowel, we move it forward. If the right pointer is not on a vowel, we move it backward. Eventually, both pointers will point to vowels. At that moment, we swap the characters. Then move both pointers inward, and repeat the same process. Once the pointers cross each other, all vowels have been placed correctly, and we're done. Let's see this in action. We'll use hello initially. LOLR, the left pointer starts at H. But H is not a vowel, so we move forward. ALOLR, now the left pointer is on E. The right pointer is already on O. Perfect. Both pointers are on vowels, so let's swap them. After swapping HOLE, now move both pointers inward. Each OLOELR, at this point, the pointers have met, which means we're done. And the final answer is whole. Notice something interesting. We never stored the vowels separately. We simply swapped them in place. And that's what makes this solution elegant. Let's compare both approaches. For brute force, time complexity O of n space complexity O of n, because we store all vowels separately. For the two-pointer solution, time complexity O of n space complexity O of 1, because we're modifying the string directly. No extra vowel storage is needed. Let's quickly recap the key lesson. Think about two pointers when 1. You're working from both ends. 2. The beginning interacts with the end. 3. You're reversing part of a sequence. 4. You want to reduce extra space. In this problem, the first vowel needed to interact with the last vowel. That made two pointers a perfect fit. And once we recognized that pattern, the solution became much simpler. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode for more LeetCode tutorials. Thanks for watching. Keep practicing. And I'll see you in the next one.